All right, welcome back, everyone. Time to get going and continue with our expert speaker session. Two more talks to go before the panel. Now it's my great pleasure to introduce our next speaker, Randell, who is currently a chair and professor at the Department of Electrical and Computer Engineering at Northwestern University. His research interests span topics in wireless communications, computer networking, network economics, and information theory. He's had a distinguished career with many recognitions in terms of research and teaching. In particular, he's an IEEE Fellow for contributions to resource allocation and interference management in wireless networks. Today, he's going to talk about cross-layer design, cognitive radius, spectrum sharing for NextG wireless. Our pleasure to have you here, Randell.
Thank you. It's great to be here. It's an honor to be celebrating this milestone. So I was thinking back. I think. So I started at Northwestern as an assistant professor around 2000. This was sort of the era of cross-layer design, and this is a little bit of a historical talk, thinking about things where my research interests and Yorgos's group's research interests touched along the way. I think my first interaction was probably doing a Murray proposal. So this is a time when UND was funding ad hoc network research, right? And there were a couple of Murray efforts that Yorgos led as an assistant professor. It was exciting to be a part of those. Unfortunately, they weren't funded, but it was still a great learning experience. And I've enjoyed interacting with him over the years, meeting him frequently at places like Asilomar and. I'd say more recently our research interests aren't quite as overlapping, so hence the more historical look. All right, so here's kind of my rough outline. I'm gonna talk a little bit looking back the two topics: cross-layer design and cognitive radio, and try to weave a thread to some of my more current interests. I'll talk a little bit about something current, which is looking at what CBRS and spectrum pooling as an idea there to improve it, and then I'll say a little bit about kind of looking ahead with in the context of spectrum, which is sort of the theme of this talk, wireless and spectrum. All right, so cross-layer design. As I said, when I started at Northwestern, early 2000s, this was kind of one of the hot topics. Everyone was looking at wireless, and this is really the time for the younger students in the audience when wireless networks were going through this transition from being traditionally a voice-centric technology to a data-centric technology. And everyone was trying to figure out what that meant, how to better support data. There were ideas, some of them that came from information theory that said that you should adapt. You should use channel state information. You should adapt to the channel. Yorgos had a lot of work along those lines. And so themes that emerged were how to think about things like scheduling different transmissions across users, accounting for channel state information, accounting for adaptive modulation, adaptive coding, and that was the type of problem I was interested in as well. And I would say again, kind of looking back while I was preparing this, it's great to see that many of these ideas are now part of things like LTE and 5G. It does this, right? There's a scheduler at the MAC layer that does these types of decisions. It gets some, sub-second, so say 5 millisecond timescales, gets information about channel states and makes these types of decisions, adapts modulation and coding. I guess the ad hoc network it wasn't quite as successful, but there's still ideas around that are coming back now with people looking at Sidelink, for example. It's a way to do ad hoc network-like topologies. And I would say this line of work was really looking at a single service provider, and kind of bridging over to the next topic that the traditional model for wireless service providers like a Verizon or an AT&T is to get large bands of licensed spectrum from the FCC, have exclusive use to that spectrum, and then within that spectrum make these types of decisions to manage the resources across their customers. So the next line of work that I got interested in, that also crossed paths with Yorgos's interest, was cognitive radio. And so cognitive radio, this was a line of work that really was spurred by claims of impending spectrum shortages that came out around the early 2000s. And again, we're hearing the same kind of claims today, that there's not enough spectrum to satisfy 4G, there's not enough spectrum, there's not enough spectrum for 6G. And so the cognitive radio theme was, there was this idea of having individual devices that could sense the spectrum and autonomously decide which bands of spectrum to use. And so in particular, one of the things it's interested in is now it's not looking at a single service provider managing their users' access to the spectrum, but perhaps multiple service providers that are dynamically sharing the spectrum, or perhaps a service provider and an incumbent federal user that are sharing the same spectrum. Modern wireless systems exhibit some of these features. I would say that this cognitive radio vision of how the spectrum problem was going to get solved, wasn't how things played out. But a lot of ideas from this you see in modern systems, but they're more at the infrastructure level. So what do I mean by that is I'll talk about next, is CBRS as an example of a system. There is spectrum sensing in there. There is the allocation of spectrum between different users, but it's not done by an individual device, like in this kind of cognitive radio view. It's done by smart infrastructure that controls devices. All right. So CBRS. So CBRS, as I said, is an example where these ideas have come together. This is a wireless system that was established in 2015 by the FCC for sharing this band of spectrum at 3.5 gigahertz among federal and non-federal users. So that the main incumbent use of that spectrum was shipborne naval radar. I think people kind of realized in one of these spectrum studies that, well, in like Minnesota or Chicago, there's not a lot of naval ships using that spectrum for their radar use. So perhaps you could share this spectrum and use it in places where naval radar wasn't present. I'll talk a little bit more. So the first commercial deployments were approved in 2019. This is being used. I can say a little bit more about it next. So the idea that emerged in CBRS is a three-tier approach for sharing spectrum. And you can think about these tiers as priority levels. So the highest tier is the highest priority, the next tier is the next highest priority, and so forth. At the top, you have what's called the incumbent tier. The incumbent tier includes naval radar. There's some other incumbent users of the spectrum, but naval radar is the most interesting one and the largest. Next, you have what's called the priority access tier. At this, the FCC ran an auction a couple of years ago in 2020 and auctioned what are called priority access licenses. So if you won one of these licenses, then it was for a county geographic area for 10 megahertz of this spectrum. And then for that 10 megahertz that you get assigned in that county, you have priority use provided the incumbent is not present. So if you're away from the coast, you pretty much have exclusive spectrum. If you're near the coast and an incumbent shows up, you have to give up your spectrum. The lowest is what's called the generalized authorized access tier. You can think about this as kind of like a unlicensed spectrum. It's not exactly, from a regulatory point of view, unlicensed, but if anyone can get approval to use that spectrum, you can have multiple entities using it as a GAA, or generalized authorized access user. All of this access, these priority levels, are controlled by this thing I'm showing here called a SAS. This is a spectrum access system. It's you can think about this as a geographic database that users have to register, check in with. And so this is where the cognition, tying back to cognitive radio, lies. It's really the SAS that's doing all of this determination of who gets what band of spectrum. It's not individual radio. And I mentioned sensing, which was a topic that Yorgos worked on with cognitive radio. Sensing is in this as well. There is these things called ESCs that stands for environmental sensing capability. And what this is it's networks of sensors that different SaaS providers deploy along the coast to detect whether there are naval ships present or not. And so an ESC informs the SaaS, yes, you can use the spectrum, no, you can't, and then the SaaS would inform the users whether the priority access or the GAA users, whether they can use the spectrum or not. All right. So we see spectrum sensing, we see some kind of adaptive resource allocation, cognition occurring here. Let me just say a little bit. So we actually had a paper last year at the Technology Policy Research Conference, which is a very different experience. It's a conference that's primarily like lawyers and economists, and a few engineers show up. But looking at how CBRS had done to date, now that it has been out for a while. And I would say it's a bit of a mixed bag. It's had some successes. It has shown pretty much, everyone who has looked at this has said that there has been zero interference to incumbents. So there's been no problems with naval radar since this has been deployed. So it has done really well in protecting the incumbents. On the other hand, it did that at the cost of some very conservative assumptions. So propagation models that were used to determine exclusion zones. Also, even though I said this is doing dynamic spectrum access, it's not very dynamic at the lower levels. So it will turn off users with regard to incumbents pretty quickly. But the PAL and the GAA users are updated what band they're operating in at most once a day. So that's not a very real-time spectrum access, and often they kind of stay put for many months. The other thing is sensing. So I mentioned there's sensing that's used. Sensing turns out to be a bit of a challenge here because, well, if you want these sensors to be detecting something, you can't have other users transmitting near them because that's going to create interference at the sensors. So basically, around the coast where these sensors are present, there are zones where you either can't transmit or you have to transmit at a lower power, which reduces kind of the utility of the spectrum in those areas. We're trying to figure out how to do sensing in a more kind of effective, robust way would help a lot. And then another issue with this is the coexistence among these GAA lower tier users wasn't really adequately addressed in the standard. So I said anyone can use this spectrum, but there's not like a Wi-Fi or listen before talk rule there. So when multiple people deploy, there's coexistence challenges that are being worked on, but to date they're a challenge. And the last issue, which kind of touches on some of my current work that I'm going to mention, is this intermittency of the spectrum is not very attractive for commercial users. So CTIA, the big group for the cellular industry, hammers this point a lot. They want spectrum that they know, or at least they can predict how much they're going to be able to use that spectrum when they deploy infrastructure. And with CBRS, the coast, you don't know that, right? You don't know what the Navy's plan is. You don't know when the spectrum's going to be there, when it's not going to be there. So one of the things, one thing we've looked at is, moving forward, if you want to use these ideas in other bands and in maybe a wider set of bands, are there ways you can help with this intermittency problem? And a fairly simple idea is well, let's kind of think about having multiple bands of spectrum available that we could pool, and then we could leverage essentially statistical multiplexing. We could say, well, if I have a set of bands and some of them aren't available, and I can, going back to the earlier part of cross-layer design and being able to allocate resources, I can shift my users to the other bands. And so if I can dynamically shift my users around, and and statistically I'm ensured that there are going to be some bands available with high probability, then it's more attractive for me to use this pool of shared bands as opposed to a single shared band that's more intermittent. And so we had a paper just last week, so this is fresh off the press, at DICE-band that looked at this and kind of characterized what's the advantage of having pooled spectrum compared to having individual bands of spectrum in a simple market model for competing service providers. So touch on that. So what we're looking at here is a model where we have service providers competing with intermittent spectrum. And I've had a line of work looking at this, and how it models these markets is using a framework of what's called Cournot competition in economics. So Cournot competition is a market modeling framework where firms compete by announcing quantities. So I say how many users I want to serve, you say how many users you want to serve, and then given the set of announced quantities, there's what's called a market clearing price that clears the market. So there's a supply curve, a demand curve, and the clearing price equates supply and demand, right? And so how do we work this into a spectrum setting is we assume that users care not just about price, but they care about the congestion of their spectrum, right? They care about quality of service. They're quality sensitive. And this congestion depends on how spectrum's shared, if it's intermittent, how intermittent it is. And so we look at cases where the market clearing price depends on both the service price that's charged to the users and this congestion cost. Okay? And so then you can look at a sort of a game theoretic model and characterize an equilibrium that I won't go into here. Here's just a little bit of math. I have a few equations. So again, there's a market clearing price. You just assume there's like a linear demand curve, and then there's a profit that depends on the market clearing price, but there's also a revenue loss due to congestion. Okay. And so to get into this idea of pooling, essentially what it's going to do is pooling is going to improve this revenue loss due to congestion if you have pooled bands versus a single band. And so we analyzed a little model of this where the congestion cost is just the users in the band over the bandwidth when it's available. And we're looking at the average loss over different realizations of availability of different bands. And then what you can show is that what a provider wants to do is essentially allocate its customers across the available bands in a way that it equalizes the congestion on those bands at any time. And that gives you a revenue loss that you can write down like this. You can look at the expected revenue loss then over the realizations of the different bands. What you get is something that's decreasing as you pool more bands given a fixed amount of spectrum. And it converges at a rate of 1 over n. And then here's a picture to show you. So this here in the blue curve is showing what would happen if you just had a single band of intermittent spectrum. And then as you increase in, you're taking that and dividing it into subbands that have independent availability. And you can see the limit is the black curve. And the other thing is that with just a modest amount of pooling, at least in this model, you approach this asymptote pretty quickly. So like here, if you had 5 bands, you're pretty close to the limit. All right. Okay, so let me stop there. That was just a quick kind of preview of some current work, and then finish up with looking ahead. So as I mentioned, spectrum was sort of a theme with cognitive radio. It's still a theme today. So I was actually yesterday, left Washington there was a presentation of this national spectrum strategy that NTIA put out. What is it saying? It's saying that spectrum is scarce, we need to share, and things like that. So all of these themes that were around, 15 years ago are still there. So, there's more spectrum sharing needed. There's some bands that are getting highlighted now. 3.1 gigahertz is an interesting band. That's a little bit below 3.5. There's also DoD radar, but it's on airplanes instead of ships. And you can imagine airplanes are a little more challenging. They move a lot faster. They cover the whole country, and not just at the coast. So there's some interesting discussions happening there. 7 to 8 gigahertz is another band that's getting a lot of interest right now from industry and from NTIA. This is a band that there are incumbents that include things like satellites. And so this is interesting questions of how do you share maybe between satellite users and terrestrial users, which is a different type of problem than we've thought about often in the spectrum sharing framework. I think there's also a lot of other things happening in this sort of overall spectrum wireless landscape now. It's not just about, cellular, mega constellations, things like Starlink. Satellite spectrum is a really interesting question, and how does satellite interface with terrestrial cellular? There's also a lot of interest in what's called private wireless networks for things like universities or factories. And how do you provision spectrum to allow for more local private uses? CBRS does a little bit of that, but there's debates over whether moving forward, should some of this spectrum be what's called locally licensed, or should it be the traditional national license of spectrum? Where's the need? Where's the uses? Another thing related to private wireless I didn't put up here is sort of indoor-outdoor uses of spectrum. There's been a lot of discussions that, where do we need the bandwidth? We typically need it when we're inside, right? When we're streaming videos, not when we're outside. And so are there ways to provision spectrum that provide that high bandwidth indoor usage and maybe allow it to be shared with other outdoor uses of spectrum? And then I'll mention O-RAN as well. O-RAN is open. RAN is a lot of interest from NTIA, from the government, as a way to open up the infrastructure of cellular networks, and potentially also has a role in sharing and addressing some of these spectrum problems by allowing infrastructure to be shared as well as spectrum. So, and then finally, coming back to more of the theme of this session, AI/ML is all over these different problems. There's lots of talk about how do you make these networks, how do you use AI and ML to share better, to manage your networks better. For some questions, last one.
Constellation plays a role? What is a mega constellation?
Well, so Starlink is a mega constellation.
Randy, repeat the question.
But the question was, what is a mega constellation? So a mega constellation is a large satellite constellation. So things like Starlink that have thousands of satellites, low Earth orbit satellites. There's Starlink is probably the most what you hear about. There's others that have been announced. OneWeb is one from Amazon. There's a few others on the horizon. That spectrum itself is getting crowded. And then there's also a lot of talk about integrating these things into cellular. So for your handheld device, when you're in a remote area and you go to a satellite instead of a cell, and that creates lots of challenges.
So for the CBRS, you mentioned the SAS, right?
Yeah.
So is it required that all the transmissions have to be coordinated by the SAS, or there is also a mode of if I detect a white space, I can have. So I'm just I'm not aware.
So currently, all devices. So you think about all the CBRS base stations have to register with a SAS and get permission from the SAS on which band.
As a transmission.
No, so that's what I was saying. It's a very slow timescale thing. So now they would register, they would get a band, and they would have that band at least for a day, probably for video.
So it's not like Wi-Fi where there is uncoordinated.
That's right.
I was wondering, in the pooling of the spectrum for the bands, there's no band-to-band interference. There's no interference issues.
Yeah.
If you go into localized allocation of the same band or pooling of resources that are reused across, then this whole framework would have to include interference.
Yes, yes.
Probably
yes.
becomes more difficult, I suppose.
Yes. So what we did was a very idealized model. There was no cost for pooling and for the subdividing. So I think there's a cost of interference across bands, and there's also a cost of reconfiguring things. So yeah, I think yes.
And interference across bands, one may argue that it's minimal, or you can minimize it.
Yeah.
But if it's in the same band, and you want to do local allocations of spectrum,
Yes.
let's say cell-to-cell, interference,
Right.
so to speak, that would be a more
That's also
challenging problem, more rich problem. Can I make one more comment? I think also in the you mentioned satellite and cellular spectral use. We also had in the Ka band for 5G frequencies in the 17 gigahertz that there's been an accommodation of satellite spectrum that can be repurposed for 5G, but can also be used for satellite feeder links. But the satellite guys get special permission from the FCC. It's another example of this problem of coordination of spectrum.
Yeah, there were some interesting things in 12 gigahertz that they were trying to get to happen that weren't successful with the LTE.
Randy, again, thank you so much for